Good morning everyone. Today we are going to see a lecture on backstepping control of robotic manipulators. So today we will be seeing the introduction of backstepping controller, and then we will use an example which is a single link robot manipulator. Then we will be moving to a special case of backstepping which is called integrator backstepping. And we will be seeing one example using the design by integrator backstepping. So, coming to the introduction part of backstepping, in the year 1990 the backstepping has been designed for the purpose of developing a stabilizing controller for a special case of nonlinear systems. The backstepping approach provides a recursive method for stabilizing the origin of a system in its strict feedback form. It provides a recursive method for stabilizing the origin of a system in its strict feedback form. It is I here. Okay. So, we will see the design of backstepping approach now. So, now let us consider a second order non-linear system in its strict feedback form given by x1 dot equal to f1 of x1 plus g1 of x1 multiplied by x2 and x2 dot equal to f2 of x1 comma x2 plus g1, okay, instead of that because it is only second order. So, we will have this coming to be u. Okay, so these are the two subsystems forming the strict feedback form of a second order nonlinear system. X1 dot equal to f1 of x1 plus g1 of x1 multiplied by x2 and x2 dot equal to f2 of x1 comma x2 plus u. So, in the backstepping approach, the variable x2 in the subsystem 1 is considered virtual control and is computed to make this subsystem that is given by equation 1 stable. Okay, so, x1 dot equal to f1 of x1 plus g1 of x1 multiplied by x2 is a subsystem 1 in which x2 is the virtual control that will make this first subsystem stable. So, let us have this control being x2d be termed as x2d, okay, and the control action u is computed so that second subsystem is stabilized, as well as the state x2 follows x2d. x2 is meant for stabilizing the system, which means that state variable x1 will follow and reach x1d, the desired value for state x1. x1d is the desired value for state x1. Similarly, x2d is the desired value for x2 state. So, the first statement is possible by having a control input which is given by x2d, because we consider x2 as the virtual control. Then for the second state x2 to reach x2d, we have the control input u to be designed. Now, with this concept, let us understand more with an help of an example of a single link manipulator. Let us consider the single link manipulator dynamics given by x1 dot equal to x2 and x2 dot is equal to minus 10 times sine of x1 plus u. So, we have first subsystem, second subsystem. So, the purpose of this is to design, the objective of this is to design a backstepping controller to stabilize the system above robotic system, which is highly nonlinear. So, the solution is, we consider x2 state be the virtual control for the subsystem 1. Let the error variable for subsystem 1 is given by E1 equal to x1 minus x1d, where x1d is the desired value or desired output of the system 1, subsystem 1. And if we choose the virtual control input as x2 is equal to minus k1 E1 plus x1 d dot, then equation 1 becomes that is subsystem 1 becomes E1 dot equal to minus k1 times E1. What do you mean by this system? This means that it is a linear system and also it is stable, which implies that for k1 positive we have E1 tends to 0, E1 becomes 0. Similarly, we have to see now for the second subsystem. So, thus the desired output for subsystem 2 becomes x2d is equal to minus k1 times E1 plus x1 d dot, and if the control input u to the second subsystem given by equation 2, that is x 2 dot equal to minus 10 times sine of x 1 plus u, is chosen to be u equal to minus u equal to plus time 10 sine of x 1 minus k 2 e 2 plus x 2 d dot. If we choose this as the control input for the second subsystem given by equation 2, then equation 2 becomes then the second subsystem becomes E 2 dot equal to minus k 2 E 2, which again implies that E 2 tends to 0 for positive k 2, that is k 2 greater than 0 values. So, in other words, we can say that x 2 tends to x 2 d. Therefore, we also say x 1 tends to x 1 d. Okay, so this is the thing, and now let us see how to generalize this concept of or the design of backstepping controller. So, we are going to see how to generalize the backstepping control algorithm. So, let us consider a nonlinear system, a general nonlinear system given by x 1 dot equal to f 1 of x 1 plus g 1 of x 1 into x 2. Similarly, x 2 dot is equal to f 2 of x 1 comma x 2 plus g 2 of x 1 comma x 2 into x 3. Similarly, x 3 dot becomes f 3 of x 1 comma x 2 comma x 3 plus g 3 of x 1 comma x 2 comma x 3 multiplied by x 4. It goes up to x m dot, which is given by f m of x 1 comma x 2 up to x m plus g 3 of x 1 comma x 2, not g m, it is not g 3, it is g m of x 1 comma x 2 comma up to x m multiplied by u. Okay, so here we can see what are the x m, x I and u. How can we say that? So, x I belongs to the n dimensional Euclidean space where I equal to 1 till m. Likewise, where x I represents the state of the system, likewise we have u belonging to the Euclidean space of dimension n is a vector of control inputs, and the functions, the nonlinear functions f I g I belonging to n cross n Euclidean space where I equal to 1 till m. These are nonlinear functions that contain both parametric and non-parametric uncertainties. And GIs are known and they are invertible. Okay, so about xi we have stated what is xi. It is basically the state of a system, and ui being the control vector, and gi fi are the nonlinear functions that have both parametric and non-parametric uncertainties, where gi is specifically known and they are invertible. So, the backstepping algorithm, we can say that they can be applied to a special case of nonlinear systems. as long as internal dynamics of these systems are stabilized. Okay. In this method of control strategy, we need to first select a desirable value of x2, possibly a function of x1. So, in this method, first we need to select a desirable value for x2. Obviously, the desirable value will be represented by x2d, which is a function of x1, such that in the ideal system x1 dot equal to f1 of x1 comma x2d, we can have stable tracking of x1 of t towards x1d. By choosing a desired value for x2 state, we can make sure that state x1 of t can track the desired value x1 of t in a stable manner. Next, then in the next step, choose x3d for the state x3 such that state variable x2 tracks x2d, and this process is repeated. That is why it is a recursive process. Eventually, we need to select the control action u of t such that the last state xm tracks xmd, the desired value for xmd. That is all. Now, let us talk about integrator backstepping. Integrated backstepping allows us to have Lyapunov function candidates in order to provide a stable control of special cases of nonlinear systems. Integrated backstepping is a special case of backstepping controller design, where the control input is connected to the system through an integrator or through a chain of integrators. Again I repeat, integrated backstepping is a special case of backstepping design, controller design, in which the control input is connected to the system via an integrator or a chain of integrators. Let us consider a system, nonlinear system, given by x1 dot equal to f of x plus g of x into lambda, where f of 0 equal to 0 and lambda dot equal to u, where lambda is known to be a virtual control. Suppose that a control law given by u equal to alpha of x stabilizes the system x dot equal to f of x plus g of x into u. We can define in continuation to this statement, suppose a control law given by u equal to alpha of x stabilizes the system x dot equal to f of x plus g of x into u. At the same time we define an error variable z, which is the difference between is a difference error signal z is a difference between the virtual control and the desired value of the control. Thus, the new variable in this case z is given by lambda minus alpha of x. Let the Lyapunov function candidate for the system 1 is given by v of x. Lyapunov function candidate for the system 1, which is represented by the equation which is x dot equal to f of x plus g of x into u. In that case, let us consider the Lyapunov function for that subsystem being v of x. Let us also consider an augmented Lyapunov function candidate be written as v a of x comma z being v of x plus half times z square. Now, taking the time derivative of this augmented Lyapunov function candidate will give v a dot is equal to v dot of x plus z z dot, which is again further expanded in the next line as dou v by dou x of f plus g lambda plus z times u minus dou alpha by dou x multiplied by f plus g lambda. We know that what is lambda? Lambda is z plus alpha of x, that can be taken from this equation. Next, substituting lambda is equal to z plus alpha of x in the above equation, we get v a of x comma z dot is given by dou v by dou x. We are simply substituting lambda by z plus alpha of x, which is given by f plus g alpha plus g z plus z times u minus dou alpha by dou x multiplied by f plus g alpha plus g z whole bracket, that can be given by dou v by dou x f plus g alpha plus z into u minus dou alpha by dou x into f plus g alpha plus g z plus dou v by dou x into g. I close it. So, this can be coming to this inequality where minus w of x, the dou v of x, dou v by dou x of f plus g alpha turns out to be this minus w of x by Lassel's theorem. So, we have less than equal to minus w of x plus z times u minus dou alpha by dou x multiplied by f plus g alpha plus g z plus dou v by dou x multiplied by g, where thus V a dot of x comma z is given by this expression, where the control signal u can be chosen such that the derivative V a dot can become a negative definite, be a negative definite. So, we have to choose a proper u in this expression, so that V a dot becomes negative definite. Let us see an example to understand this concept of integrated backstepping controller in a better way. Let us see an example here. So, consider the following system: x1 dot equal to minus x1 cube plus x2, which is given by equation 1. So, x2 dot equal to x2 square plus u, which is equation 2. Now, design a suitable controller that can stabilize this system. Okay, so, we need to go by integrated backstepping controller to stabilize the system. So, as per the solutions, we have the following steps. Solution contains few steps, say step 1. So, in this problem Ex2 can be treated as the control input to subsystem 1. Now, define a virtual control alpha for the system 1 and an error variable z such that z is equal to x2 minus alpha 2. Okay, so we can say this as alpha 2. Okay, the solution starts with select x2 being the control input to equation 1 or subsystem 1. Now, define a virtual control which is given by alpha 2 for subsystem 1, and also define parallelly an error variable z such that z is a difference between the control input and the virtual controller. So, equation 1 becomes x1 dot is equal to minus x1 cube plus z plus alpha 2, because I am representing equation 1 in terms of z, okay, because z is equal to x2 minus alpha 2. Now, going to step 2, let us go to step 2. Define a Lyapunov function candidate for subsystem 1 such that v of x1 is equal to 1 by 2 x1 square. This implies that v dot of x1 is equal to x1 dot. Substituting the x1 dot from equation 1, we can have x1 multiplied by minus x1 cube plus z plus alpha. This can be equation number 4. Now, step 3 is select a virtual control, that is alpha, which is equal to minus k1 x1, where k1 is greater than or equal to 0. The step 3 is select a virtual control such that alpha equal to minus k1 x1, where k1 greater than or equal to 0. So, this implies v dot of x1 given by minus x1 power 4 plus x1 square minus k1 x1 square, which is equal to minus x1 power 4 minus k1 x1 square plus x1 z. I just exchange the terms 2 and 3. Let us have this equation as equation number 5, and alpha dot can become minus k1 into minus x1 cube plus x2, that is 6th equation. Let us move on to step number 4. So, here the virtual state equation that is in terms of z dot is given as z dot equal to x2 dot minus alpha dot, which can be written further as x2 square plus u minus alpha dot. So, x2 square plus u in alpha dot, when we substitute, we have plus k1 into minus x1 cube plus x2. This is equation number 7. And finally, we have step 5, the augmented. We have seen about the Leibniz candidate for system 1, subsystem 1, and we also stated about the virtual equation with alpha value. Now, we can see step 5, where we can have the augmented Leibniz function candidate. Augmented Leibniz function candidate being chosen as V a of x comma z equal to v plus half z square. So, V a dot becomes v dot plus z dot. Upon substituting what is v dot z dot, we will be having V a dot expression being minus x1 power 4 minus k1 x1 square plus x1 z plus z multiplied by x2 square plus u plus k1 times minus x1 cube plus x2. So, this term is v dot. Likewise, this term, the second term, is coming out to be the z dot term, this term, not the complete, z multiplied by z dot. So, z dot term is given by that. So, which can be further written as minus x1 power 4 minus k1 x1 square plus z times x1 plus x2 square plus u plus k1 multiplied by minus x1 cube plus x2. Thus, step 6 will be targeting to select a proper u. So, u to be chosen such that V a dot is negative definite, which will make the second order system stabilizable, which will make the second order system stabilizable. So, I will also give the simplest form of the control action u for our problem. Example 1 is, say, u equal to minus k2 z minus of x1 plus x2 square plus k1 multiplied by minus x1 cube plus x2. So, this will make the system stabilized. This can be further simplified into minus k2 multiplied by x2 plus k1 x1 minus of x1 plus x2 square plus k1 multiplied by minus x1 cube plus x2. That is all. So, in this lecture, I have come to a conclusion now, come to the conclusion part now. So, we have seen a simple design of backstepping algorithm, and we have also seen in this lecture a special case of backstepping called integrator backstepping controller, where we have used, for each subsystem we have used individual Leibniz candidate functions in order to stabilize the entire nonlinear system. Thank you very much for your patience. With this, I stop here.